Everyone. A warm welcome to all present in this meeting. On behalf of the Department of Mathematics at Wilson College, Mumbai, I heartily welcome Mr. Gaurav Sawant sir for his first session in this IIT JAM Mathematics lecture series organized under the DBT Star Strengthening Scheme. Sir is an assistant professor in the Department of Mathematics at Veermata Jijabai Technological Institute, which is VJTI in Mumbai. His areas of interest are in algebra, analysis, geometry, topology, and number theory. The topic of Sir's sessions would be ordinary differential equations. Sir, we are grateful to have you today with us. Over to you, sir. Thank you.
Thank you, Miss Madhavi, Miss Bridgie, and Miss Tina, and everyone else at Wilson College for inviting me for this particular sessions. So, without further ado, let me share my screen or the window rather. Yeah. So, there are, I think, a total of 9 or 10 topics in ordinary differential equation that are typically part of syllabus for IIT JAM. So those topics are, as mentioned on the screen: separable differential equations, orthogonal trajectories, homogeneous differential equations, exact differential equations, integrating factors, Bernoulli equations. So these first six topics, that those are mentioned from 2 to 6 in the list, those typically cater to first order ordinary differential equations, and the topic 7, 8, 9, second order differential equations, variation of parameters, and Cauchy-Euler equations. They deal with higher order differential equations. I have mentioned a miscellaneous as a list item, which, uh, well, I decided to keep certain equations as unclassified, and well, some of them can be done through separable and so on and so forth. So that we will see when the time comes. So the plan is that I'm going to cover these 4 sections today. Just mention the dates. Then the session on the second session, which will be done tomorrow, that will take integrating factors and Bernoulli equations. Mention them that way. And then, like the way, like we will see how we progress, and the second order things and some of the miscellaneous will be done on the third and fourth day, and we'll see how that goes. So everyone fine with this plan? Firstly,
Yes, sir.
Yes,
all
sir.
right, all right. So let's begin. Okay. So what does it mean by an equation being ordinary differential equation? Okay.
The-
So typically, when you have one variable as free, one variable dependent on that free variable, and then the derivatives of this dependent variable um, involved in the that particular equation. So it will typically have the form some f of x. So I'm assuming x to be the free variable and y to be the dependent variable, which will be treated as a function of x. So y dy by dx, and potentially higher order derivatives as well. Y dx then equal to 0. So I have written it in an implicit form. So this is a typical nth order ordinary differential equation, where n is this particular thing. And you will see that it is ordinary because there are no other derivatives involved. For instance, as opposed to partial differential equations, where you would have certain variables. So a partial differential equation would be of the form x1, x2, xm, let's say. So these are the dependent variables, dependent on a free variable, let's say t, and then you would have like partial derivatives with respect to all these variables. So you would have some. Let me write. Let me just not worry about this at this time because we are focusing on ordinary. So there is only one like a dependent variable y, one independent variable x. You could have x t, y t, and so on other combination, but the derivatives are only of one function. So our first order differential equations are typically going to have a form which can be written as dy by dx equal to some f of x, x, y. Okay, so when, so the like most important question is that when will such an equation make sense and when will it admit a solution? So there is a theorem attributed to Picard which says that theorem by Picard. So let me quote it directly. Let fxy and the partial derivative of f with respect to y be continuous function on a closed rectangle R. Then through each point, not y naught, in the interior of R, there is a unique solution. Dy by dx equal to fxy. Uh, yes. So what turns out to be the role of this particular point is that it is an initial condition. So you would have the function f x y evaluated at this point giving a certain value. So given this particular point x naught y naught, I will have a certain value of that. With that initial condition, I will have the Picard theorem says that this will have a unique solution. So we are not going to really worry about the theorem and its proof per se, but we are going to actually look at certain things in action. Okay, so let's move on to types of first order differential equations.
Sir, here R means like any rectangle.
So on some closed
When
rectangle
it is
R.
continuous, like on some closed rectangle, if we take where the
So
function del f by del y is continuous, that will be okay, right?
yes, yes. So on some closed rectangle. So let's say my axes are like this. I could let's say have it defined on maybe this much of a rectangle. It is possible that some other function could be like it could be continuous on maybe only this much. Maybe it is possible that entire x greater than 0, y greater than 0 is being covered. But there is, for closeness, you also have to consider the limiting part. So maybe not a good idea, make it like this. And so on. There are several possibilities. But it has to be a closed rectangle. Okay.
So,
So
like we cannot say about the solution of a solution on boundary points, right?
yes, so there are some issues at the boundary points because the derivative, this partial derivative or even this like total
Okay.
derivative, these are typically defined on the interior because
Yes, yes.
by definition they need to have the right limit and left limit equal, right?
Yes, sir. Yes, sir.
This as a function has to be continuous. So
Yes.
that is why those derivatives are typically not properly defined on the boundaries, but we will not worry about that.
Okay, sir.
We are not going for the proofs as such. We are actually going to see these things in action. So let's move on. So typically, I have mentioned these few like types here, right? Before. So separable, homogeneous, exact. Okay. And also linear. So that linear thing I have not mentioned here, but it will come somewhere. So this we may see if possible. Let's move on. So what does it mean by a separable equation? Separable differential equation. So if you notice, we had in Picard's theorem statement, we had dy by dx equal to fxy, right? So if this particular function is of the form, let's say some phi of x plus some psi of y, where you can write the right hand side as a sum of a function of x and a function of y. So in that case, you say that you can separate the variables, and hence the name separable differential equation. And then this gets converted to you can take the y terms on one side, x terms on the other side somehow. No, not plus, sorry. It has to be a multiplication. Psi 1. In this case, what we can do is we can divide throughout by this psi, assuming that this psi is not 0 at some point, and we would write dy over psi y equal to psi x dx. Okay, and then we can simply these are just one variable increments, and then you can simply take integrals on both sides, and you would have integral 1 over psi y dy equal to integral psi x dx. And of course, there will be some additional constant that you may need to adjust sometime. So there may be cases where these integrals are not elementary or may not be very easy to solve, but in most of the cases they are, and you can simply get a suitable solution. And you will get an explicit solution, you will get an implicit solution because on this side there will be some function of y, on the other side there will be some function of x plus constant, and you take them on the other side and you will get something equal to constant in an implicit form. And when you put the initial conditions, the initial conditions are y of x not equal to y naught. So if that initial condition is put, you will be able to find the exact value of the C constant, and thereby you will get that thereby you will get that unique solution. Okay, so let's see a very straightforward. Okay, we'll see the example a bit later, but we will talk about some. Then there is another type of differential equations that is called homogeneous differential equation. Let's say of degree k or degree n. So these are again of this the same form, dy by dx equal to fxy, but so I will call this thing as 1. So 1 is called homogeneous of degree n if I scale these uh, variables x and y by a scaling factor t, and it essentially jumps outside with that particular power. So if f tx ty becomes t power n fxy. So most of the time you would actually see degree 0 or degree 1 homogeneous differential equations in most of the problems, and those are fairly easy to handle too. Okay, there is another kind of first order differential equation which is called an exact differential equation. So when we have an equation of the form dy by dx equal to fxy, if this can somehow be transformed into the form mxy dx, let's say, plus nxy dy equal to 0. So let me like rewrite that fxy here, given the form that I have mentioned here. So it will be minus mxy over nxy. Okay, so if this mxy dx plus nxy dy equal to 0 is the form the differential equation is given in case, so this is exact if the partial derivative of m with respect to y is the partial derivative of n with respect to x. So how does that really work? So it turns out that if I have something like, so this works because let's say I have some capital phi xy, an implicit function, implicit equation of this form. And if I take the total derivative on both the sides, I would have del phi del x plus del phi del y equal to 0. On the other side, there is a constant, so it will just run out. And you will have dx dy. So these turn out to be the total derivative. So this function is your m, and the other function is your n. And then in like partial derivatives, you have this condition that mixed derivatives are equal as long as the function is like twice continuously differentiable and satisfies certain conditions. So you would have um, del x del y is equal to del y del x. And this is essentially the same condition that is mentioned here. Del m by del y equal to del n by del x. And then these can be solved in a very straightforward manner also. That you would pick one of m and n, integrate them with respect to the suitable variable. So in this case, m would be integrated with respect to x, and would be integrated with respect to y, and you will get suitable uh, like constants or certain like independent functions, and then you take the other derivative and find the uh, and then equate that with the remaining guy from m or n, and then find the answer. Okay, and then you would have linear equation. So recall that I had mentioned the general form as f x y and y dash. I'm only talking about first order differential equations, so only the first order derivative will appear. So this equation is called linear if this expression is linear in terms of x, y, y dash, as in it is a linear combination. So typically, when we think about linear combinations of something, you would have constants multiplying those objects. But here we allow functions also to multiply. So you would have the form as, let's say, y dash plus p x y plus 2x, or equal to 0, or maybe I will just use some change of signs and make it in this. So this has to be linear in y. Right. So like these functions px and qx, these are like functions of x alone, and the linearity is in the combination. So the linear combination is of y dash, y, and 1, which is kind of hidden here. Okay.
Yes, sir.
Yeah. And then there is yet another type, which is a like anything that cannot be like exactly expressed in this particular form is a nonlinear differential equation. And then there is a special class of nonlinear differential equations that is called the Bernoulli equations. And these will have a form. So the left hand side looks the same, but the right hand side has a power of y in front. So n not equal to 0. Uh, Maybe n not equal to 0 or 1.
0, comma 1.
Yeah, not equal to 0 or 1. Because if n is equal to 0, then it just becomes a linear equation with in the above form. If n becomes equal to 1, then I can just take it as a y dash plus px minus qx times y equal to 0. So this is the fifth type. Okay. And there are some other types which I'm not going to go into right now. So let us look at these equations in action and have some interesting problems from previous year question papers. So let me move this thing over. It will be just drag that question and resize it correctly. All right, so everyone can see the question clearly, right?
Yes, sir.
Yes, sir.
Okay. So in like these questions, like sometimes the language is just such that it can confuse you. So always see whenever there is a slope mentioned, that is the derivative dy by dx. And whenever you are having something passing through the curve passing through the point, this always corresponds to the initial condition. And this is dy by dx. Okay, so let's have a look at this problem. So the differential equation here is dy by dx equal to sin x over x square minus 2y over x with the initial condition. So you have this as x comma y, right? X naught comma y naught. So y of pi by 2 equal to 1. All right. And let me for simplicity write that dy by dx as y dash. Okay. So turns out this problem is actually fairly easy to handle. Can anyone see how this goes?
Yeah,
Yes,
is
sir.
it linear?
It is linear.
Yes. So one quick way of doing this is just transfer this y over x term on the other side and multiply throughout by x square. So what you get is x square y dash minus 2xy plus 2xy that came on the other side equal to sin x. Okay. But then notice this side. So this is actually a chain rule derivative kind of situation happening here. So note that d by dx of x square y is x square dy by dx plus y dx square dx, which turns out to be the left hand side of this equation. So x square y dash plus 2xy, right? So then I can simply convert this in the form x square y whole dash equal to sin x. And note that now this is in a separable form because on one hand I just have dy by dx or some dz by dx, whatever you want to call, and on the other hand you just have a function of x. There is no function of y or x square y involved. And then you can simply integrate both sides and you will get x square y equal to sin x dx, which is equal to minus cos x plus a constant. And then we use our condition, initial condition, y of pi by 2 equal to 1. Okay, so we have x square y equal to minus cos x plus c naught, which gives me y equal to minus cos x plus c naught over x square. Substitute. So this y, although I'm mentioning it as y, it is actually y of x. So substitute y equal to 1, x equal to pi by 2, because it is mentioned that the curve passes through that point. So we go ahead with that substitution, and we should get 1 equal to minus cos pi by 2 plus c naught over pi square by 4, which tells me 4 over pi square is equal to c naught. Right? Right? Is that correct, everyone?
Yes, sir.
Yes.
Sir, I think
Or
there will be
is there
pi
something?
Sir, it
Price
shouldn't
No,
be
no, no.
pi
That,
square by 4.
it will not invert. That is correct. So
The
people
pi
are,
square by 4 would
yes,
be.
yes. So good. People are not sleeping in the lecture. So great. So therefore we have obtained this. So solution x square y equal to minus cos x plus pi square by 4. And then you take that cos on the other side, and you will have, this is the same thing as x square y plus cos x equal to pi square by 4. And if you see, there is exactly one option that satisfies. So everyone okay with this?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. Now let's look at a relatively easy problem. Okay. So maybe on a new page. Okay, why am I not able to drag it? I lost track of that. Okay. Yes, everyone is able to see the problem. Okay, now this is a fairly straightforward question, right? So when I have this equation, I just have dy by dx equal to minus alpha y, which has the straightforward solution yx equal to y naught e power minus alpha x, right? And then since my y0 is equal to 1, I don't need to bother about this. So yx is equal to e power minus alpha x is the solution. And now that you have the solution, you simply check the option, these given options, and see which one is appropriate. So the moment there is an exponential function and nothing else around it, you are absolutely sure that this function is not going to be equal to 0 ever. So already the first option is gone. Then if you see, I have e power minus alpha x, and alpha is a real number. So whenever this alpha is a positive real number, I am going to have the solution just decay to 0 as x goes to infinity from wherever I start, whatever my, so my y0 is equal to 1. It's the only like concern is how fast it is going. So I have this y not equal to 1. So this is 0, this is 1. I would have, for some alpha, I will have this kind of decay. For some other alpha, I may have this kind of decay and so on. So these are only for alpha greater than 0. If alpha less than 0, then this is just going to increase like crazy. And I will have things happening like this. So this is alpha greater than 0. And if alpha equal to 0, then this guy is just going to stay at the constant value 1. Right? So if I see whenever alpha is greater than 0, all the solutions are going to 0. So there is no longer a unique alpha. So this option is also out of the window. Then I have a potential condition of y2 equal to 1. So it turns out, we have already seen here, that when alpha equal to 0, I will have constant function 1 as the solution, and that would satisfy y of 2 equal to 1. But then this option claims that there is no such alpha. So this option is also gone. And then we end up having this option. And it turns out that I can choose my alpha to be equal to minus natural log of 2. Which will give me y of 1 is equal to 2. All right. So far, so good.
Yes.
Okay. Let's look at a multi-select problem. So as everyone knows, there are 3 types of problems in a typical JAM question paper. One is a multiple choice type question where you will have only one answer correct. Then there will be a multi-select question where you can have multiple options out of 4 correct. And then there is a numerical answer type question where you have to provide your answer in like rounded up to as many decimal places as requested. All right. So this is a multi-select type where I have been given the differential equation in this form and with the initial condition. So as you can see, again, this is a separable equation. So I can actually take these this function of y on the other side and x on this side, right side, and have dy over y minus 1, y minus 3 equal to dx. Now a quick look tells me that I can use partial fractions to break this into simpler objects. And essentially, I will have to find the constants a and b such that a over y minus 1 plus b over y minus 3 equal to 1 over y minus 1 y minus 3. Right? Then you would see that this can easily be broken and like these constants can be found and they turn out to be a equal to minus half, I believe, and b is equal to half. Okay, and this converts. So people please quickly verify that I am doing it right. If there is any mistake, you have to immediately let me know. Okay, so if you go about this, I will have half dy over y minus 3 minus half dy y minus 1 equal to dx, which readily simplifies to half log y minus 3 over y minus 1 is equal to x plus some constant, which simplifies to y minus 3 over y minus 1 equal to some other constant times e power 2. All right. And then with suitable rearrangement, no, before doing the suitable rearrangement, you have to input the initial condition y0 equal to 2. Y0 equal to 2. So when I put that, I would get 0 minus 3 over 0 minus 1. 2 minus 3 over 2. Sorry. Is equal to C2. So that is just equal to minus 1. And I will have y minus 3 over y minus 1 equal to minus e power 2x. And this can actually be played around with and converted into the final form y equal to e power 2x plus 3 over e power 2x plus 1. Okay. So now the options.
Explain this step.
Yes, what?
Can you explain this step, last step?
Yes. So I would have y minus 3 over y minus 1 equal to minus e power x. Yes. Okay. Let me just work it and so think about it. Okay. Just working it out on a separate paper so that I can tell you.
Well, I think if we substitute y in the given equation, we will get minus e raised to 2. You mean to say that?
You actually just wait. Yeah, but this is not given. What happened? What happened? Let me think about it. Just a minute. You people keep working on this. Let me also take a fresh paper and try to do this. So let me just correct this. Check this out.
So we get y equal to this one, e raised to 2x plus 3 by.
Yes, you get right.
Yes, sir.
Yeah. So it is only up to certain rearrangements you will have to work on. So that now that you have this y equal to, okay, Where is my pointer? My pointer also wrong. Okay. So now that I have this, I just have to check which of these options are valid, right? So I already see that there is this form. I check for the limits as x goes to plus infinity, x goes to minus infinity. So when I send x to plus infinity, I'm going to get a limiting form of e power 2x over e power 2x, which actually gives me the limit as 1. So this third option is already correct. Then when I take the limit to minus infinity, this e power 2x, e power 2x, these terms are going to 0. I will be left with 3 over 1 format, which will give me equal to 3.
3.
So this option is also correct. And then since there is an exponential involved, uh, this denominator is never going to be 0. Okay. So, and the numerator can go haywire. But then I have both ended limits existing, which tells me that the function is bounded. See, for this y to be unbounded, there is a numerator by denominator kind of thing. Either the denominator has to be equal to 0 or the numerator should go to infinity somewhere. But we have already seen that the only place where the numerator could have possibly gone to infinity, there the denominator is killing it. And otherwise this denominator is never going to be equal to 0. So that is why from the options A and B, only B is correct. So B, C, D are the 3 correct options for this. Okay. Any questions about this?
No, sir.
No. All right. Okay. So, Miss Madhavi, are you there? Or anyone from Wilson College? How long can I go?
So you may continue. I mean, how long do you need?
Uh, okay. So I will go on for maybe a 15 minutes extra because we started late. So I think that much is fine.
Yeah, no problem. No issues, sir.
Okay. So next we move on to an interesting topic, which I had not mentioned in the types of differential equations, but it comes along with. So let me add a page. Okay. So this topic is called orthogonal trajectories. So the word orthogonal clearly means that something is perpendicular to something given, right? So let's say I have some function like this drawn in black. So any function that intersects this black curve orthogonally. So anything that goes like this, as long as it is intersecting orthogonally, that would be a trajectory or a function orthogonal to the given function. You could also have families of orthogonal trajectories, or orthogonal families are as they are called. So I could have, let's say, circle centered at the origin. That is a family of functions. And as everyone knows, the radii or diameters extended into their respective lines, they will always be perpendicular to these. So, okay, where is mine? Okay. So anything like this, anything like going straight. So it has been constrained, just assuming that it has anything coming like this. All of these are perpendicular to the black curve. So these straight lines will end up being orthogonal trajectories, or trajectories orthogonal to the family of circles. Okay. So we have this straightforward result from our elementary school geometry that whenever I have two perpendicular lines, okay, one of these lines has slope m1, other line has slope m2. Then, so these are slopes. Then m1 times m2 is equal to minus, right?
Yes,
So
sir.
we will actually use this idea to talk about orthogonal trajectory. So I have this function uh, y is equal to fx or some form. So what I know that at any point x naught, if I draw the tangent line, so the tangent line will always have slope equal to the derivative evaluated at the point x naught, right? So let's say that is m1. So if something is some other curve is intersecting orthogonally at that particular point, then the corresponding slope, so anything, any other curve which is tangent here, so that slope will exactly have to be equal to minus 1 over this dy by dx. So if uh, a function or curve uh, let me call this curve as script c1. Let me write it in a different way. Suppose that a curve c1, which is given as x f x, x y x. We are using y. Intersects another curve c2 equal to uh, so I will not write the equation of this curve ortho at or orthogonally at a point x naught y naught. Then the slope of c2 at x naught y naught is equal to minus 1 over dy by dx at x. So how to actually put this in action? So you would have a typical sometimes curve, sometimes a family of curves. They will be given as an implicit expression. So f xy equal to 0 or fxy equal to c, something like that. Okay. So the idea is you do an implicit differentiation with respect to x. With respect to x and rearrange. So, okay, that's the second step. Rearrange in the form dy by dx equal to some fxy, small fxy. All right. And then, so this particular value dy by dx is the slope of the tangent line at, let's say, some point x naught, y naught for this. And then the orthogonal trajectories or curves which are orthogonal to this given curve or family of curve. That is why. So 1 over, so minus 1 over dy by dx. So that is minus dx over dy equal to the same function. Okay. So what we will do is we will look at some interesting examples of orthogonal trajectories, and then we will stop the session for today, and then we will reconvene tomorrow. So let's look at some examples. Okay. So okay, so we have the equation or a family of curves y equal to c1 x cube. Okay, right? So therefore, I have the so this particular family is going to satisfy. So dy by dx is equal to 3c1 x square. Correct? But
Yes.
then what is c1? That c1 is actually satisfying the equation, right? Y equal to c1 x cube. So I have c1 equal to y over x cube. So this I substitute here and I will get 3y over x. So dy by dx equal to 3y over x is the differential equation that the original family of curves should satisfy. So the thing is that we always have to eliminate all these constants. So this is the original family. So if we want to find the differential equation of the orthogonal family, uh, you only have to make the reciprocal of the left hand side and attach a minus sign. So trajectories satisfy minus dx over dy equal to, the right hand side remains the same, 3y over x. But then you see, this is a very straightforward separable form, right? So I can simply take this on the other side and have minus x dx equal to 3y dy, which readily becomes minus x square by 2 equal to 3y square by 2 plus c. C is some constant, and then I can take x square by 2 on one side, on the right side, c on the left side, flip around and multiply it by 2, and I will end up having x square plus 3y square equal to constant, some other constant. So you actually have that here, and that's your answer. Right?
Yes, sir.
Yes.
Okay. So let's have a look at something interesting. So I will have this is the penultimate problem for today, and so and then we'll have just one more, and then we'll be done for today. Hmm. Okay, where did my pointer? Okay. All right. So just an interesting observation. Let me just put this a equal to 1 for the time being. So that particular curve, x power 2 by 3 plus y power 2 by 3 equal to a power 2 by 3, or in this case a equal to 1, is called an asteroid because its graph looks like a star of some sort. So the graph kind of looks like this. Okay. So anyway, so I have this expression written in an implicit form, right? So I just do an implicit differentiation throughout by x. So essentially, I will start with d by dx, x power 2 by 3 plus y power 2 by 3 equal to d by dx power 2 by 3. And when like on the right hand side, it is just a constant, so it will be equal to 0. On the left hand side, I have 2 by 3 x power minus 1 by 3 plus 2 by 3 y power minus 1 by 3 dy by dx equal to 0. This readily rearranges to dy by dx equal to minus x minus 1 by 3 over y minus 1 by 3, correct? But then these x power minus 1 by 3 is 1 over x power 1 by 3, and similarly the y thing. So that converts to y power 1 by 3 over x power 1 by 3. Correct?
Yes, sir.
Yes.
Yes. And so this is the original family. So the orthogonal trajectory are going to solve the differential equation minus dx over dy equal to minus y one third over x one third. So these minus signs will go away, and again this is a separable form. So I will have x 1 by 3 dx equal to y 1 by 3 dy. and which readily solves to equal to 2 by 4 y power 4 by 2 plus some constant. I will just put a C naught for the time being. And then I take that y power 4 by 3 on other side, multiply throughout by 4 by 3, and then take a suitable power of that constant to get x power 4 by 3 minus y power 4 by 3 equal to some suitable constant c power 4 by 3. So that turns out to be this one. Okay. Finally, so we'll move on to, we are going to do one last problem for the day. Okay, so now I have a question in this form. Same deal as always. So for the family F, I will do an implicit differentiation again, right? So when I do the differentiation, what will I have? So let me just write the steps. So dx x square plus 2hxy plus y square equal to, on the right hand side, I'm just going to have a 0 because there was just a constant, right? So what do I have? I have 2x plus, now h is supposed to be a constant, so it will not be really affected by this derivative, but I will have 2hy plus 2hx dy by dx plus I have a y square, so I will get a 2y dy by dx equal to 0. So I take all the terms involving dy by dx on one side. Actually, I don't, I will just combine those two terms and just write them in the beginning. So I would have dy by dx, and I will actually throw out divided by 2 as well, the same time. So I will have hx plus y plus x plus hy equal to 0. I have just like combined those terms and divided throughout by 2. But then I have to still eliminate the h, right? And that can be done by observing that x square plus 2hxy plus y square is equal to 1, right? So I can write 2hxy equal to 1 minus x square minus y square, and therefore h is equal to 1 minus x square minus y square over 2xy, correct? That is what we are going to substitute there, so that dy by dx. So I will have 1 minus x square minus y square over 2xy, and then there is an x here, so 2y plus y plus x plus 1 minus x square minus y square over 2x equal to 0. And then it is mere simplification now. Dx. So I will have a 2y square getting added. So hold up. Hold up. Wait. Yeah. So the thing is that I will let this be like this for the time being. 1 minus x square plus y square over 2y plus x square minus y square over 2x equal to 0. Let's rearrange a bit. Equal to minus of 1 plus x square minus y square over 2x divided by for that term 1 minus x square plus y square over 2y, which I am going to write as reciprocal 2y 1 minus x square plus y square. And that is it, equal to minus. So on the in the numerator, I am going to have 2y plus 2x square. Anyway, that 2 is going away. So y plus x square y minus y cube, and that took care of the numerator. In the denominator, I have x minus x cube plus xy square. Right. So this is the equation of the original family. Right. The original family is satisfying this differential equation. So therefore, the orthogonal trajectory will satisfy minus dx over dy is equal to this object minus y plus x square minus y cube divided by x minus x cube plus xy square. So just flip it, dy by dx equal to x square over y plus x square y minus y cube. So take this y plus x square y minus y cube on the right hand side, and then subtract x minus x cube plus xy square, and then you will get the answer. And when you look at the options provided, it turns out that A is the right. Okay.
Yes, sir.
Yes.
All right. So I think this should be it for today. And tomorrow, I think, will it be okay for everyone to start at 5:30?
Yes, sir. For me, this
Okay,
will be okay.
so 5:30 is fine for everyone, right?
Yes,
Okay,
sir.
so what we can do is we can have a 5:30 to 7:30 kind of a longish session, so that we can cover as many
Okay, sir,
more
no
problem
problem.
types as possible. Okay.
Sir, I have a question. Can I ask now?
Yeah, sure.
Sir, whether I don't recall that whether you have explained why we just mechanically it is all right that we put that dy dx and flipping those things and ultimately getting the orthogonal trajectory. But my question is why this flipping occur? Because orthogonal trajectory means both the curve are intersecting orthogonally. That is
Yes.
why, that is why if M1 is the slope of the curve C1 and M2 stand for the curve of C2, then it is those tangent who are making 90 degree to each other. That is why
Yes.
M1 and M2 is equal to -1. But
Yes.
why we replace? I think I would replace the M2, that is
Hmm.
the orthogonal trajectory is that point. This should be replaced with the dward of slope of M1. But
Yes.
in this equation directly how can I put this and getting the solution?
Okay. No, no. So what is happening is that I will
Yeah,
have the original family or original trajectory. Let me use a different ink. So okay, where is it? Yeah. The original trajectory is C1, and let's say it at a particular point, the corresponding slope is dy by dx. So that is
yeah.
my M1. Okay. So
Hmm.
yeah, this is not a constant, it is a function, but anyway.
Yes, sir.
So I have M1, M2 equal to -1. So M2 is definitely going to be a -1 over dy by dx, right?
Yes, yes, sir.
Yes. So if this essentially was like initially change in y with respect to x, but now it turns out to be change in x with respect to y.
Yes,
That is why that became equal to minus dx over dy.
yes, sir. And we replace just dy by dx to this value because these two are the same now.
Yes,
And from that, getting the solution of the orthogonal trajectories. That is okay, okay.
yes, yes.
Okay, sir. And sir, whatever you have, due to some technical problem, I am joined it too late.
Mhm.
And whatever in the topic covered, I am following you from the Euler equation, that is Bernoulli. From that point, I
Okay,
am
okay.
following.
Okay, sure. So the thing is that the like I have sessions for 4 days, right? Today, tomorrow, and next Saturday, Sunday. So
Okay,
after these like 4 days, I will share the PDF of this particular like writing to
okay,
the authorities, and then they will forward it to the Telegram channel and how.
okay, sir. Thank you, sir.
Okay. Okay.
Sir,
Brigitte,
do
ma'am,
you have any YouTube channel where I can follow you?
yes, pardon, I didn't get you.
Sir, do you have any YouTube channel where we can also follow you?
No, 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 I don't.
Okay, sir.
Are there any further questions, suggestions?
No, sir.
No, sir.
Okay.
Sir,
All right. So if there are no more queries, we have come to a close of today's session. Thank you so much, Gaurav, sir, for this engaging session. We are looking forward to your further sessions as well.
Mm,
Uh, Thank you,
sure.
participants, for taking out your time. This is a weekend, so you'll have come eagerly to learn uh, in this series. Thank you so much. Thank you so much, everyone.
Thank you.